On our previous lesson, we have started something about law of conservation of momentum, and as you can remember, according to this law, we can consider, for example, we can consider collision between two rigid bodies. Collision between two rigid bodies. For example, with velocities v1, v1 and v2, and if we have absolutely elastic collision, in the result of this collision, according to the law of conservation of momentum, we have that momentum after collision is equal to momentum before collision, which is equal to momentum of first body plus momentum of the second body. So this is sum of momentums. So according to the law of conservation of momentum, the momentum before collision is equal to momentum after collision. And what does it mean? As we know from practice, from everyday life, that as a result of collision, these two bodies will be heated. They will be heated, so their temperature will increase. But how to calculate? This heating, this increasing in temperature? Momentum doesn't allow to do this. Because of the law of conservation of momentum. So it means that we have to consider some more physical values, and according to our experience from practice during many centuries and even thousands of years, this new physical value is energy. And before learning energy, we have to define a new physical value that is known as work of force. Maybe you can remember from school. That for simple system, when we have a plane surface, which can be drawn like this simple plane surface, and some body on this surface, and if we have a force that is impressed on this body, force F that is impressed on this rigid body, maybe you can remember from school that for this system we can define work of this force. We can define work of this force according to the formula, where A is work. This is work. That is signed by letter A. Letter A is first letter of from Deutsch word arbeiten. Arbeiten means work in Deutsch. So this is equal to F force multiplied by path and multiplied by cosine of this angle alpha. Angle alpha between the direction of motion and force. Okay, and now we have to generalize. We have to generalize this formula from school, to generalize this formula for any type of trajectory, for any type, and for any line, not only for straight line. So how to do this? We can do this using calculus. We can choose very small part of the path and define work for this infinitely small part of the path. We can define this with formula f cosine alpha multiplied by ds, and this can be written in another form. Maybe you can remember from kinematics that infinitely small path is equal to length of length or modulus or absolute value of infinitely small displacement vector. So we can write this in another form. We can write this as f modulus and multiplied by dr. dr is infinitely small displacement vector multiplied by cosine of alpha, and according to the vector algebra, this is equal to dot product, or which is the same scalar product. Vector dot product or scalar product f dr. Scalar product. Okay, so do you have any questions about this? No questions. Okay, and no. Yes, thank you. No questions. Okay, and to define and calculate work for the whole path of motion, for the whole path, we have to integrate this value. So we have to take integral. And we can obtain from here a formula. This is integral or along the path S, integral along the path S, f cosine alpha multiplied by ds, and this is equal to integral from R1 to R2 f dr. This is line integral. It means that it depends not only on initial and final position, and it also depends on path. It also depends on path from initial to final position. So it is necessary. It is necessary to take into account in general case. Okay, and let's write it in one more form. As you can remember from kinematics, this can be and vector algebra. It can be written as f can be written in projections of vectors fx dx plus fy dy, and this can be written as oh, no, plus fz dz, dz. Oh, it means that we obtain another form of this line integral. So we can write this as according to this formula. And this is general formula for work of a force. We can write that this is work of a force. Work of a force. Work of a force. It can be calculated. It can be calculated with this formula. With this formula. And the physical unit for work is joule. And 1 joule, 1 J is equal to 1 Newton multiplied by 1 meter. 1 meter. And sometimes, not sometimes, often it is necessary to know not only work. Often it is necessary to know velocity of producing this work. Producing. So in other words, it is necessary to know the derivative of the work. And this physical value is known as power of work. It is known as power It is known as power, and it is equal to first derivative of work by time. Work by time, and but I have cleaned some necessary formula. dA is equal to F ds cosine alpha, and this is equal to F dr, and this is equal to F dr. So we can substitute this here, and this will be F ds by dt cosine alpha, and this will be equal to F. This will be equal to F dr by dt. dr by dt. And now, now it is necessary to remember kinematics. And from kinematics, we can remember that derivative of path by time is equal to absolute value of velocity, and the derivative of displacement vector by time, or radius vector by time, is equal to vector of velocity. So we can write that power of a force can be calculated with formula dA dt is equal to force modulus of a force multiplied by modulus of velocity multiplied by cosine of the angle between vectors f and v, and this is equal to scalar products of vector f and vector v, where v is velocity. This is power of a force. And unit for power is known as watt. 1 watt is equal to 1 joule divided by 1 second. So what is joule per second? Joule per second. So this is work of a force and power of a force. And this definition of definitions of work and power allows us to define energy. How to do this? according to the formula of work of a force, we have that work is equal to linear integral R1 from R1 to R2 f dr. And according to this, we can rewrite this formula. As we remember, the second Newton's law of motion, we can write that m derivative of velocity, and this is equal to f. We can use this here. We can use this here. And in this case, we can write that R1, R2, R1 and R2, and this is equal to, and here we have, here we have this, and multiplied by dr, and we can make some changes in this formula. Mass is a constant. So it can be written outside the integral. It can be written outside the integral. So and we can change. We can change parts of dot product. Parts of dot product, changing of places does not affect our result. So we can write this as dr dt multiplied by dv, and we have changed differential. We have changed differential in integral. So it means it means that we have to change integral limits too. So it is necessary to write v1, v2, v1 and v2, and as you can remember from kinematics, this derivative is equal to velocity. This is equal to velocity. So it means that it is possible to write this as m multiplied by integral from v1 to v2 v multiplied by dv Okay, and the next step is to calculate this scalar product. And how can we do this? We can do this in the next way. we can draw a picture. We can draw a picture. dv is vector v, vector of velocity. dv is change of this vector or increase of this vector, and we can consider dv is as a sum of two vectors. According to kinematics, we can consider dv as a sum of vectors, sum of vectors dv tau and dv n and dv n and dv n, and this is right angle. This right angle. Okay, so what do we have from here? We have that v multiplied by dv is equal to v multiplied by dv tau and plus v multiplied by dv n multiplied by dv n and according to this we have that here the direction of v and dv tau is the same, so we can rewrite this as v multiplied by dv cosine dv tau cosine 0 and plus v multiplied by dv n cosine 90 degrees, and this term is equal to 0. This term is equal to 0, and this is equal to 1. So we can rewrite this as v multiplied by dv tau. But we know that dv tau is change of the modulus of velocity. dv tau is change of the modulus of velocity, and it means that this is equal to dv. It is a result from kinematics. So this will be v dv. So in initial for origin, for initial case, we have v vector multiplied by dv vector, and the final result is modulus of v multiplied by modulus of dv. So this can be written as m multiplied by the integral v dv, and from v1 to v2. And this integral can be easily calculated. It will be m v2 squared divided by 2, minus m v1 squared divided by 2. Divided by 2. Okay, do you have any questions? No questions. No questions. Okay. Okay. If there are no questions, I need to clean some place. I need to clean place on the screen. I need to clean some place, and from here we have that we can sign this. We can sign this as key 2, and this we can sign as key 1, and this physical value key 1 key 2 is known as kinetic energy. This is kinetic energy. This is kinetic energy. So we can write here that kinetic energy of any system of material points. Here is kinetic energy for one material points, but if we have a system of material points, we can calculate the sum. This will be m I v I to the power of 2 divided by 2 and of course this is always more or equal than 0. It is necessary to know kinetic energy is always non-negative value. Always non-negative value. So this is kinetic energy. Kinetic energy. Kinetic energy. Kinetic energy. Kinetic energy of any system of material points. Any system of material points can be calculated with this formula. Can be calculated with this formula. Can be calculated with this formula. Okay, so I think I will clean some place. I will clean some place on the screen and how to do this. How to do this. Here I will I will use this. I will use this next time. So this is equal. This is equal to key 2 minus key 1. Key 2 minus key 1. We will need this. We will need this later. We'll need this later. We will need this later. Okay, so do you have any questions? No questions. Okay, let's continue. Let's continue. For work, we have a formula. We have a formula. The work A is equal to linear integral from R1 to R2, or from R1 to R2, and here we have integrand that contains of force and infinitely small displacement vector dr. Okay, this integral is a quite difficult mathematical problem, but fortunately, fortunately, often in many important cases, it is not necessary to calculate this. Let's consider the case. Let's consider the case if consider the case if f is equal to const. Let's consider the case when f is equal to const. In other words, force f doesn't depend on position. Doesn't depend on position in space. Doesn't depend on position. In this case, we can write f outside the integral. Outside the integral. So we can write that this will be integral from R1 to R2 dr. And this will be f multiplied by R2 minus R1 minus R1. So as we can see for this case, work depends on only initial and final position. Depends on initial and final position, but doesn't depend on path of transition. Doesn't depend on path of transition, and it is very important. And in this case, if f is equal to const, we have so-called homogeneous field. Similar situation we have in so-called central field. Central field is also very important case because for example electrostatic field that we will learn, and gravity field they are potential fields. They are potential fields. What is potential fields? Potential field is a field of forces where work doesn't depend on path of transition. Work in potential field depends only on initial and final position, and not doesn't depend on path. So for potential fields, we can we can write work. We can write work. We can write work with this formula for potential fields. U in position R2 minus U position R1, where U is a function that depends only on position, and U is new physical value. So this new physical value that is known as potential energy. And it is necessary to say that force that allows to force which allows to write work with this formula, force which allows to write work with this formula is called conservative force, and the field of conservative forces is a potential field. It is necessary to understand. It is necessary to understand this. Okay. And examples of potential fields are homogeneous field, and central field. And for example, electrostatic field and gravity field are potential fields. So for electrostatic field and gravity field, we can use potential energy. So for potential field, we have formula. For potential field, we have formula. We have this formula for potential field. Okay, and how to calculate potential energy? How to calculate potential energy? We can do it in this way. We can do it in this way. We can write a general formula for work. R0 is initial position. R is some position in space. F is some conservative force. dr, and this will be equal, according to this formula, this will be equal to minus U as a function of R, potential energy as a function of R, potential energy as a function of R, and minus U0, where U0 is potential energy in initial position. And this value U0 and the initial position R0, we can choose as we want to. We can choose any value we want to choose, because work depends on only difference of potential energies. So we can choose R0 and U0. We can choose them. And from here we have that potential energy. Potential energy can be calculated. It can be calculated with this integral. It can be calculated from a force. Can be calculated from a force with the formula. With the formula F dr vector dr and plus u0 plus u0 and one more we can choose any value of r0 or u0, but it is necessary to say that we should choose such values that make formula as simple as possible. That make formula as simple as possible. So because it will be more useful. It will be more useful to choose to choose simpler formula. And so here we have potential energy. Potential energy. Potential energy. Potential energy. And it is necessary to remember that potential energy can be used only for conservative forces. Only for conservative forces. For example, it cannot be used. It can be not be used for force of friction. Force of friction, because work of force of friction depends on a path. Depends on path, because for example, if the path is a straight line from point 1 to point 2, the work of a force of friction will be one value, and another value we will have if we have this path. So works of force of friction will is different for different paths. So work of force of friction is not conservative force. So for force of friction we cannot define potential energy. Okay, so now I have to say a few words about some important practical cases of potential energy, because this formula is not used very often. Because it is inconvenient. So let's have a look. Let's have a look at a few interesting practical cases. The first example is gravity force near the surface of the Earth. Near the surface of Earth. Earth is our planet. It can be proved that in this case potential energy can be calculated with a simple formula mgh. where m is mass, g is acceleration of free fall, and h is height. H is height. In this case, we have that height of initial position, is 0, and u0 is equal to 0. So potential energy of body in homogeneous gravity field. This is one important practical case, and the next important and commonly used case, that potential energy of deformed spring. It can be calculated with formula K, where K is a spring constant. We have learned this previous week. K is a spring constant. X is elongation or extension of a spring to the power of 2 divided by 2. This is potential energy of deformed spring. And this potential energy of body in a homogeneous gravity field. Okay, do you have any questions about this? No questions. No questions. Okay. So let's now let's consider a general case. When we have motion. When we have motion under different forces. That include conservative and non-conservative forces. Conservative and non-conservative forces. We can write this. In the next way. From here we have that this will be integral from R1 to R2 m d v by dt dr, and this is equal to the integral of R1 from R1 to R2, and this will be FC dr plus the integral from, this is vector value, R1 to R2 F d R. Okay, and how to calculate these integrals? As you may remember from as you may remember from here, as you may remember from here, as you may remember from here, this first integral is equal to kinetic energy in final position minus kinetic energy in initial position. This integral is a work of conservative forces. Work of conservative forces can be written as minus potential energy in final position minus potential energy in initial position. And this is work of non-conservative forces. This is work of non-conservative forces. Non-conservative forces. This is non-conservative forces. Okay, and from this we can write that now I will explain that we can write that E2 minus E1 is equal to work of non-conservative forces. Work of non-conservative forces. Is work of non-conservative forces. And what are A1 and A2? E1, E2. E is mechanical energy or whole mechanical energy. It is so it is the same as key 2 plus U2 minus key 1 plus U1 plus U1, and this is equal to A. So mechanical energy is sum of kinetic and potential energies. This is K plus U. K plus U. Sum of kinetic and potential energy. Kinetic and potential energy. And this is so-called work energy theorem. This is work energy theorem. 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 Mechanical energy and work energy theorem. Work energy theorem. And from here we can from this theorem we can obtain the law of conservation of mechanical energy. Law of conservation of mechanical energy. So if law of conservation of mechanical energy, of conservation of mechanical energy. Law of conservation of mechanical energy. So if there are no or if there are only conservative forces, conservative forces no if there are only conservative forces, we can write that E, all mechanical energy, is equal to const. Is equal to const. A law of conservation of mechanical energy. Law of conservation of mechanical energy. Hey, do you have any questions about this? And according to this, we can say that if there are some non-conservative forces, mechanical energy will change. Mechanical energy will change, but the whole physical energy, whole energy of the system, of course, will be constant, according to the law of conservation of energy. But mechanical energy may change, because it may transform into other forms of energy. For example, heat energy or electric energy. And I have forgotten something to say. This formula may be written in other way. I will not prove this. I will only show the final result. We can use calculus. To do this, but I will show only the result. From here we can write that F for potential field force may be calculated as minus gradient of U, minus gradient of potential energy. So it is the same as d by dx I plus d U by d y j, and plus d U by d z k. Uh, Force can be calculated. Force can be calculated from potential energy. From potential energy with this formula. Force can be calculated from here. Calculated from here. From here. And it is necessary. It is necessary to say a few words. It is necessary to say a few words about dynamics. About the dynamics of rotational motion. About dynamics of rotational motion. About dynamics of rotational motion. But I will clean my screen. I will clean my screen because now we don't need this formula. Okay, dynamics of rotational motion. Let's imagine a simple door. Simple door, and let's look on it from above. Look on it from above. Okay, we have door. Here we have door. Simple door. This door can be rotated. Can be rotated in this way. In this way, and you know that if we put a force upon it, if you put a force upon it, the angular velocity of rotation depends not only on this force, but it also depends on this distance. Also depends on this distance between this force and the axis of rotation. It depends. It also depends on this distance. So we can define very quickly a few physical values for understanding dynamics of rotational motion. The first is torque. Torque or moment of force. Torque. And what is torque? Torque moment of force. Moment of force related to the point. Related to the point. Torque related to the point. Torque or moment related to the point. This is a vector product or cross product of R and F. R and F, where R is a radius vector that begins in any point on axis of rotation and ends in a point where force is impressed. So this is moment of force related to the point. Related to the point, or maybe it is better. Maybe it is better to to write to a point, weighted to a point. Okay, but sometimes, not some, often it is not it is not convenient to use torque related to a point. Um, it is more convenient to use torque related to the axis of rotation. Related to the axis of rotation. What does it mean? What does it mean? I'll try to draw a simple picture. Let's imagine that Z is an axis of rotation. Axis of rotation. Here we can draw perpendicular from axis of rotation to some point to some point where force is impressed. So this is perpendicular. This is R. This is R. This is R, and here we have the projection of a force on direction that is perpendicular to the screen, or that is perpendicular to plane that contains R and Z. So F perpendicular. F perpendicular. In this case, we can define torque or moment of force related to the axis of rotation. To an axis of rotation. An axis of rotation. It can be written in this way: M Z is equal to cross product R and F perpendicular. F perpendicular. And according to the properties of vector product, we can define the direction of this vector. The direction will be here, mz. And what about modulus? Modulus of this torque can be calculated in simple way. It will be just simple product R F perpendicular. And because of this, this torque is useful. For many practical cases and exercises. Okay, and another value is necessary to define is a pair of forces. What is this? Pair of forces. these are two forces with the same value, pair of forces with the same value, but they act along parallel lines. Along parallel lines, and the distance between these forces is known. This is d, and it is necessary to calculate momentum, torque for this pair of forces. Torque or momentum of pair of forces. The direction here, the direction will be perpendicular to these forces, and it is from us to the screen, and in this case we have that this torque or moment of force of force of forces and this is m equal to f multiplied by d. Simple formula. Simple formula that is used used very often. And of course, in a very similar way, we can define angular momentum. Angular momentum can be defined in a way that is very similar to defining torque. For example, angular momentum related to a point. Angular momentum related to a point. The formula are very similar. To previous, but it is necessary to change force with momentum. So this will be L. L is equal to R multiplied by momentum P, and this will be M multiplied by R velocity V. And very similar to this angular momentum or angular momentum related to an axis of rotation. Related to an axis of rotation. Related to an axis of rotation. So LZ is equal to R multiplied by P perpendicular, And this will be the same as mass multiplied by R multiplied by V perpendicular. V perpendicular. And the absolute value is equal to this. And this will be RP perpendicular. And this will be MRV perpendicular. MRV perpendicular. V perpendicular. Okay, so I think that this is enough for today. Do you have any questions? No questions. No questions. Okay, so thank you for your attention. Thank you for your attention, and I hope to meet you next week. I hope to meet you next week.